Okay, welcome back, and today we're going to finish up chapter 8 by talking about probability distributions and expected value. Just like I said before, that hey, if we know that a population has a particular distribution, or we're dealing with a particular probability distribution, um, then we can use that to our advantage, and it makes calculating probabilities and calculating other things about the population or about the um, what we're talking about easier. Okay, if we don't know anything about the population, then we just have to use our probability um, definitions that we learned in the previous sections. Okay, so in this case, we're going to talk about different probability distributions and how they can help us, and we're also going to talk about what an expected value is. So a random variable. A random variable is a variable, right? So it changes from object to object. So it could be height, it could be weight, it could be color. Anything that changes from object to object, subject to subject is a variable. Now, a random variable is just a variable where the outcomes are basically decided by a random process. Okay? For example, the outcome when you pull the lever on a slot machine is a random variable, right? The blood type of a randomly selected individual from a population is a random variable, because if we're just randomly choosing somebody by using some random process, then the outcome of their blood type is going to be random. It's a variable, right? Because blood type changes from person to person. So those are what we're going to be talking about. Those are the things, those are what we're going to call random variables. Okay, so now a probability distribution is just a table. That's it. It's a table of values where you have the possible outcomes, also along with their corresponding probabilities. That is a probability distribution. Okay, so this one here is a discrete probability distribution where you have all of the possible outcomes for x. So x could be either 0, 1, 2, 3. So these are the probability distribution for broken monitors in a sample. So you take a sample of monitors and you find that either you're going to have one broken monitor, two broken monitors, three broken monitors, or two broken monitors or three. So notice that the total sample that they're taking here is 3. Okay, so the number of broken monitors. So if you have a shipment of 12 computers, so let's say in this example here we have a shipment of 12 computer monitors contains 3 broken monitors. A shipping manager checks a sample of 4 monitors to see if any are broken. Give the probability distribution for the number of broken monitors that the shipping manager finds. Okay, so, well, X represents the number of broken monitors. So if we're looking at a probability distribution for the number of broken monitors, well, we have maximum number of broken monitors, 3. Okay, so if he randomly selects monitors, well, he's either going to find 0 broken monitors, 1 broken monitor, 2, or 3. Can't have more than that. So now, what's the corresponding probability? Well, if 0, how many, if he, what's the probability that he finds none? Well, how many monitors are not broken out of the 55? Okay, well, let's see. He's going to take a sample of what? Shipment of 12, right? And contains 3 broken monitors. Okay. And, well, how do we figure out the probability? How do we get that 14 out of 55? Because that doesn't look right, right? Well, you're thinking, well, there's only 12 monitors. How do you do that? Well, think about this. This is where, okay, how many different ways can he get 0 broken monitors out of how many is he choosing? He's choosing 4. So this is a combination type problem. So you're going to have to know your combinations and make sure you know how to use the function on your calculator. So again, you're going to need to know how to use, where is it at? You're going to have to need to know to use these two functions on your calculator. So you're going to have to use nChooseR for combinations. So NCR for combinations, or if it's a permutation, you need to make sure you know how to use NPR. So make sure you know how to use these two keys or these two functions on your calculator, okay? Because in this case, it's combinations because the manager doesn't care the order in which he chooses the monitors. All he cares about is once he chooses his 4 monitors, how many of the 4 are defective. So these are going to be based in combinations. Okay, so you're going to need to make sure you know how to calculate these probabilities. But once you calculate these probabilities using what we know in the previous sections, then all you do is plug it in. So this is an example of a probability distribution. Okay, and to get a probability distribution, it's only a table. You list out all the values of x, and then you list their corresponding probabilities. And notice that we know that this is a probability distribution because if you add up all of the numerators add up to what? 55. And so you get 55 over 55, which is 1. So this is a valid probability distribution. Okay, now, so let's look at this example. It says a shipment of 12 monitors contains 3 broken monitors. A shipping manager checks a sample of 2 monitors to see if any of them are broken. Find the probability distribution for the number of broken monitors. Okay, so here's what we're going to do. You start with your table, right? So one side is going to be x. The other side is going to be p of x for the probability of x. Okay, and so what do we have? We have 0, 1, oops, or 2. Okay, so we got 0, 1, or 2. And so this probability here, what's this probability? Since we're dealing with combinations, right? Oh, by the way, well, let's think about this. Okay, so we're selecting well, let's see, we're selecting 3, right? So we're selecting 2 out of the 12, and we want to know what's the probability of having 0 that are broken. Okay, so we want the probability, right? Okay, so let's see here. We want to know 0 are broken out of the 2 that we picked. Okay, so how do we calculate this probability? Well, this is going to be equal to I'm just going to do the first one, and then you'll have to do the rest of them. So what's the numerator? Well, how many different ways can we choose 0 of the broken monitors out of what? The 3. Okay, how many broken monitors how many monitors are we choosing? We're choosing 2, right? So we're choosing 2 monitors, and of the 3 that are broken, how many do we want to choose? 0. Now, that leaves what? The rest of them that are not broken. Well, how many of them are not broken then? There are 9. And of the 9, how many do we want to choose? Well, we want both of them, 2. We want the 2 monitors that we're choosing to not be broken. Now, how many different ways could I choose 2 monitors out of all of the 12 monitors? Well, that's going to be 12. Choose 2. And this is what's going to give us the correct answer. Now, notice that to get the rest of them, all we're going to change are these 2 numbers. This 0 and this 2 are going to change. So for 1, it would just be, this would be a 1, and this would be a 1. And for the 2, this would be 2, and this would be 0. And that's it. That's how easy it is. So I'll let you do that. And again, practice that. And so we're going to let x be represent the random variable, the number of broken monitors found by the manager, and the possible values for x are 0, 1, and 2. There are 3 broken monitors and 9 unbroken monitors. So the number of ways of choosing 0 broken monitors, which implies that the 2 unbroken monitors, which implies two unbroken monitors, is this: 3 choose 0 and 9 choose 2. And then the total number of ways of choosing monitors is 12 choose 2. Okay? And so these are the results. Okay? Easy peasy lemon squeezy, as my now 9-year-old daughter says. And so this is the probability distribution, and that's all you would need to do. Okay? Now notice that if you add these up, it adds up to 1. So this is 12 out of 22. 12 plus 9 plus 1 gives us 22. Okay? Now, say it says find the probability distribution and draw a histogram for the number of tails showing when 3 coins are tossed. All right, here we go. So we want the probability distribution. So let's get the probability distribution first, because to draw a histogram, we need the distribution. So, okay, so we're flipping a coin, or we're flipping 3 coins, right? And so when we flip 3 coins, we want to count the number of tails. Well, what are the possible number of tails that we could have after tossing 3 coins? Well, we could have no tails, which means what? All heads. We could have 1 tail, which means 3 heads. We could have 2 tails, which means we'd also have 2 heads. Or we'd have 3 tails, which means no heads. And then we want the corresponding probability. Now, we could do, oops, sorry, wrong one. Let me erase this. Oops. Okay, so we could do this 2 different ways. We could use the probability. So let me set up the first one, right? So we could say probability of 0. Okay, the probability of getting no heads, or excuse me, no tails, is what? It's a combination, right? So how many different ways can I get no tails? Well, that would mean what? Hold on. So that would mean that out of the tails, out of the 3 coins that I tossed, how many tails did I get? 0. Okay, times how many heads would I have to have? Well, I only have 3 coins, right? So of the 3 coins, I would have 0, right? So that's the combination of how many different ways can I get 0 heads out of 3 coins, right? Now, how many different combinations can I get for the flip of a coin? How many different ways can I get heads and tails? Well, in this case, order is going to matter, right? Because if I have 3 coins, right, there's a first coin, a second coin, and a third coin. Okay, so it's going to be a little bit different with this one. Now, so I'm going to have to use permutations. So when I use permutations, I'm going to say, okay, well, how many ways can I get 0 on the probability table here? Well, also, first of all, think about the experiment. You have 3 coins. You're tossing 3 coins. The probability of getting a heads, the outcomes on the first coin are heads or tails. The second coin is heads or tails, and the third coin is heads or tails, right? So there's only 2 possible outcomes for this experiment, right? Also, each coin is independent of each other, right? The first coin doesn't affect the probability of the next 2 coins, and so on and so forth. And what are we interested in? Well, we're counting the number of tails out of the 3 coins, right? Right, and the probability of tails doesn't change from coin to coin. So this is a binomial experiment. So look what we're going to do. So if I say, how many different ways can I get how many possible outcomes are there for the coins? Well, if I look at the permutations, right, it's going to be what? I get 2 times 2 times 2, which is going to be 8. Right? So I get 8 possible outcomes, right? Because I get heads, 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 tails, heads, tails, heads, heads, tails, tails, right? And then I can just repeat the process with just beginning with tails, okay? So what's the top here? Well, I could get, if I'm looking at 0 heads, well, or excuse me, 0 tails, that means I got all heads. How many ways can I get just all heads? Well, there's only one way, right? Because if I have 3 choose 0, and then that means I get 3 choose 3 of the other kind. Well, this is 1 and this is 1, and you just get 1, right? Or if I want the probability of getting 1, then again, this is an easy one because I can just write out the sample space. I know there's 8 possible outcomes, right? But this is also a binomial experiment, so I know that, hey, how many different ways can I get 1 heads? Well, that means of the 3 coins, right? How many different ways can I get 1? Right? There's only how many ways? 3. Where is it? So here, there's only 3 ways to get 1 tail. So that's going to be 3 out of 8. And then this P of 2 is also going to be 3 out of 8 because of the symmetry of the binomial distribution. Okay, and then the last one will be 1 out of 8, which adds up to 8 out of 8. So we can get that one way, but also this is a binomial experiment. Okay, so we could count up the total number of outcomes. So we could do that from earlier sections, earlier chapter 2, and just use the definition of probability, and we can do 1 out of 8, and so that's easy to count. Or we can use the fact that this is a binomial distribution and use the formula, and that can also give us the probabilities. Either way, we'll get the same probabilities. Okay, so let's erase this and move on. So in this case here, it says let x represent the random variable, the number of tails. So we can have 0, 1, 2, or 3. And then we can find the probability of the outcomes. Okay, and so we can either use the binomial probability, or notice that there are 8 outcomes, again, and we just count up the outcomes that give us exactly what we're looking for, exactly 0, exactly 1, exactly 2, or exactly 3. Okay, and so we're going to get this probability distribution. So now the histogram, that's what we calculate afterwards. So to create your histogram, all you do is you create your two axes, x-axis and your y-axis, which is going to be probability, and you label out your tick marks, and you just basically put out your probabilities. Now I would do the, if you want to do the eighths here, okay, or you could do the decimals, okay, it doesn't matter. And then here, what you do is, since these are discrete, like whole numbers, then all you're going to do is put a tick mark in the middle of each bar. So you're going to just put your tick marks evenly spaced and just put 0, 1, 2, and 3. And then what you're going to do is you're going to draw your rectangles, and you want to make sure all the rectangles are about the same width. If you do it on the calculator, which I'll show you how to do on the calculator, very easy, it's automatic. But if I ask you to sketch one out on paper, then just make sure that the bars are evenly spaced, and that they touch, and that the bars are about the same width. Okay, because again, look at the width of these bars. These are all 1 unit width. The heights of the bars correspond to their probability. So all you have to do is draw a rectangle at the height of the probability. So at 0, you're going to have a probability height of 1/8, and then 3/8, and then 3/8, and then 1/8. And notice how it's a nice symmetric histogram. Okay, so again, you have to make sure they're touching. Okay, so here's another histogram. Now this one represents, let's see here what it represents. Let's see here. Oh, this is the probability distribution of the computer monitor one. Okay, so if we took this probability distribution here, where is it at? This one. This is a similar one, probability distribution for the monitors, but this one here is the one where you're selecting 4 monitors. Okay, so you're selecting 4 monitors, and your probability that 3 of them are defective, or the probability that 0, 1, 2, or 3 are defective. So here's the broken monitors. So this is an example of a histogram, and so you would also have a title here, but again, we already know what this is. But if you were making these, you would have a title so that your audience knows what this represents. Then you'd have broken monitors as your x-axis, and then probability as your y-axis. So here's the distribution. So notice that the probability of having 0 broken monitors is 14 out of 55. Having 1 broken monitor, 2 broken monitors, or all 3 of the or 3 out of the 4 broken monitor being broken. Okay, and so this is an example of a histogram for that example. So now, okay, so this is just it without the numbers. Okay. Now notice, let's see here. I'm seeing if there's anything that I should say about this one. Um, Oh, okay, I see what it is. Okay, so what this is here, if you look at it, so this is just each individual probability. Okay, but what if we wanted to ask a question like, what's the probability of finding at least one broken monitor? Okay, so a histogram not only gives us the distribution, so we can actually see the shape of the distribution here, and we can see where the largest probability is of getting at least one broken monitor has the largest probability. So we can easily see and get information from a histogram. But we could also answer questions like, for example, what's the probability based on this histogram that we get at least one broken monitor? Well, what does it mean that we have at least one broken monitor? Now, this goes back. Think about what we've talked about probability, right? At least one means that we either have one, or we have two, or we have three, right? So or means what? Addition. So what we're going to do is we're going to take this probability and this probability and this probability here and add them up. So if we add these up, what do we get? We get 31. Or no, excuse me, 41. So you get 41 out of 55. So that's what this distribution. So this shaded region here, this pink, represents the area under the curve that's going to be our probability. Because if you think about it, this rectangle has a base width of 1 and a height of its probability, right? So the area of this rectangle actually represents probability. And the area of this also represents probability. So we could say that the area of these three rectangles gives us the 41 divided by 55. Okay, and that's the answer to that question. Okay, now here's the probability for the distribution of heads. So let's look at what we're doing here. So this says give the probability distribution for the number of heads showing when two coins are tossed. So again, we can list out the four possible outcomes. We can get a heads and a heads and a tails and a heads, or a tails and a tails. And so we can easily construct our probability distribution at 0 is 1/4 because there's only one way to get 0 heads, which means both tails. There's one way, right, to get, there are two ways of getting heads, one heads out of 4, so that gives us a probability of 1/2. And then there's also just one way of getting both heads. So this is our probability distribution, and it is also symmetric. Okay. And so if we look at the histogram, look at the histogram here. So if we say, hey, what's the probability of getting at least one heads out of flip of two coins? Well, what's the answer? It's going to be this plus this, which is going to be what? 3/4. So 75.75. Okay, so that is the probability of getting at least one head on the flip of two coins. Or if you say, hey, what's the probability of no heads? Well, that's going to be the complement of that, which is 1/4. Okay, so because all of this has to add up to 1, right? Okay, now let's talk about expected value. Now, expected value is an industry term. The expected value is none other than the average outcome for a probability distribution. What is the average outcome? For example, what's the average of a probability distribution? Okay, what's the average outcome? Okay, so it's the mean. So this is the none other than the mean, okay, that we're going to be calculating. Okay, so how do we calculate the mean of a probability distribution? This is the formula that we're going to use. Okay, and so this is a formula. I'm going to show you how to do it. And now this is it's written out, but realize that this is very similar to the formula for the average of a data set. Okay, so if we want the expected value, which is just the average, okay, so again, this is used in insurance. It's an industry term, so we can say, hey, what's the expected outcome on a sale? What's the expected loss on a business deal? What's the expected winnings? Expected winnings if you go to the casino or play a game. What's the expected what's the expected life expectancy, right? Life expectancy, what's the expected value for the number of years that somebody will live? So these are all, whenever we say expected value, what do we expect the outcome to be? It's say, hey, if we do this experiment over a long period of time, or we do a large number of trials, what is the average outcome that we're going to get? That's what we mean by expected value. It's a long-term outcome, the expected outcome if we were able to do this over and over and over again. Okay, so the formula for expected value, okay, is also given shorthand using sigma notation. And so what this means is that what we're going to do is we're going to take the sum of the products. Okay, so this is sigma notation. So it says we're going to take the sum of all of the products of X okay, times its corresponding probability. Okay, so we're going to take all of the products. We're going to take basically the value of the random variable times its corresponding probability. We're going to take all of those products and add them up, and that's the average. That's the expected value. Okay, that's what we're going to do. So if we were going to find the expected winnings, so here's a game. So what's the setup here? Okay, so it says, let's see here. Let me see which one we're doing. Okay, so it says here we have a game that we're playing. Or no, not a game. It's a symphony orchestra. It says, suppose a local symphony decides to raise money by raffling an HD television worth $400, a dinner for two worth $80, and two CDs worth $20 each. A total of 2,000 tickets are sold at $1 each. Find the expected payback for a person who buys one ticket in the raffle. Now, how much are the tickets? The tickets are what? $1 each, right? So now, if we're thinking about this, so let's set this table up. The way we're going to set this up is what are they asking? What is the expected payback? Okay, which means that you're going to be paying $1 for the ticket, for the raffle ticket, right? So that means all of the prize money needs to be reduced by $1 because we're talking about net gain. Right? So we're talking about payback. So we're talking about the net gain on this. Okay, so we always subtract the out of pocket, right? Or this is the net cash flow if you want to think of it as cash flow. So it's the money that's coming in minus the money going out. So you paid $1 for the raffle ticket. So if you bought one raffle ticket, you're down by $1 already. Okay, so the probability distribution for X is the net gain that you are. So if you win the first one, which is $400 set, then your net payback, your payback is $399 because you paid $1 for the ticket. And likewise, the 80 is going to be reduced to 79, and the $20 ones are going to be reduced by $1. Okay, and then if you don't win any of those, then you lost $1, and so you're negative $1 net. Okay, and then your corresponding winnings is there's only one TV set, so of the 2,000 raffle tickets that could be chosen, it's going to be 1 out of 2,000 tickets. The probability of winning the tickets is going to be 1 out of 2,000. The probability of winning DVDs is going to be 2 out of 20,000 because there are 2 of them. Okay, so again, if you win those, then you've got a net payback of $1, or excuse me, $19. Okay, and then of course there are 1,996 other ways because there are 4 prizes that they're choosing for, and so that means that there are 1,996 ways of not winning any of those. Okay, and so this gets us our probability distribution. So now, how do we calculate the expected winnings? Well, here's how we do it. Okay, so what I would do is using the table, you just multiply down. Okay, so the expected value of X, the expected winnings, is going to be what? It's going to be $3.99 times 1 out of 2,000 okay, and then I'm going to do 79 times its corresponding probability, which is 1 out of 2,000. And then I'm going to do the next one, which is 19. And that's going to be a probability of 2. Out of 2,000. And then, of course, I could get a -1, and that's going to be 1996 out of 2,000. And then all you have to do is plug and chug. And that's where you're going to get your answer from. And so if you plug and chug, let me calculate this. Okay, so we get $3.99 divided by 2,000 plus 79 divided by 2,000 plus 19, hold on, so it would be 38 divided by 2,000, and then it's going to be minus 1996 divided by 2,000. And if we were going to do raffles, so here's the idea. If you were going to do raffles over and over again, and so you did the same raffle over and over again, right? And you paid your dollar over and over and over and over again for a long period of time. And of course, you're going to win some, you're going to lose some, and this and that. But after all of this time, let's say you did this 10,000 times, what would your expected earnings be? Well, it's going to be negative 74 cents for every game, for each game, which means that on average, if you did this 1,000 times, you would lose what? You would lose 74 cents every single time. Okay, basically, you'd lose $740 of your money if you did this 1,000 times. Okay, so not a good deal. Okay, probably not something. Same thing if you were going to use this for like gambling. What's your expected winnings if you play the roulette wheel every single time for a long period of time? Okay, you can actually look those up. It's not good. Okay. Okay. So now, what about this one? What do we have here? So we have each day, Donna and Mary toss a coin to see who buys coffee, which is $1.20 a cup. One tosses and the other calls the outcome. If the person who calls the outcome is correct, the other buys the coffee. Otherwise, the caller pays. Find Donna's expected paycheck. So here we go. Here we go. Donna's expected payback. Okay, so here are the results. So here's the results of the tails. So heads, 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 tails, right? So, and then the caller wins. Yes. No, no, yes. Notice that, hey, all of these probabilities are equally likely. So what do you think the net outcomes are going to be for this one? Well, you're paying $1.20 for a cup of coffee, right? So, and all of the outcomes are equally likely. And so, yes, she wins. No, she doesn't. No, she doesn't. Yes, she does. So it looks like she's going to break even, right? Try it out, test it, prove it, see if I'm correct. Use this information, and what's the outcome? So yes. So this, if it's yes, she basically, in a manner of speaking, she gets $1.20. If it's no, she loses $1.20. So do the calculations. Her net payback will be zero. Okay. Why? Because it's a fair coin, right? It's 50-50. Chances of winning, right? You're just guessing, right? And so the chances of getting a heads and calling the right number is pretty much a 50-50 shot. Okay, so each one has a fourth of a chance of winning. So you could get this one or this one, which adds up to these, right? 1/2. And if you add these two probabilities, that adds up to a half. You get a 50-50 shot, 50-50 chance. Okay, so now what about binomial probability? If it's a binomial experiment, guess what? The expected value is just the number of trials times the probability of success, n times p. Okay, so the expected number of successes out of n trials is just the number of trials times the probability of success. That's it. So if we have this one, so this is the distribution for the number of girls. And so this is a binomial experiment because what we're looking at is we're saying, hey, let's see here. Where is it at? So we're looking at, suppose a family has 3 children. Okay. And it says find the probability distribution for the number of girls. So obviously you can have, just like the coin tosses, you can have heads or tails. So you can have boys or girls. So if you have 0 girls, that means all boys. So it's 1 out of 8. So notice that this has the exact same distribution as we saw with the tails example when we had 3 coins and we wanted the number of tails. Okay, it's the exact same distribution. So now if we use this distribution, we can calculate using the binomial probability. This is a binomial probability by the way. You can see that's a binomial probability, but if you think about it, it's easy to see, right? Each girl, each child is either going to be a girl or boy, right? So there's only 2 possible outcomes. You only have 3 children, right? So there's a fixed number of trials. Whether one child is a girl or boy doesn't affect the probability of the next child being a girl or boy. And the probability of being a girl or a boy is the same, 50-50. So this is a binomial experiment, which means that the expected outcome for the expected number of girls in this case is going to be n times p. The probability of getting a girl is 1/2. Okay, so the probability of getting a girl is 1/2, and the number of girls or the number of children there are is 3. So half of 3 is 1/2. So the expected number of girls is 1/2. And that's the answer. And again, you could use the general rule. You could use the definition of expected value, and you can use the other formula. It'll give you the same answer. Or you can use the fact that this is a binomial probability, and it's just n times p, where n is 3 and p is 1/2, and you get the same answer. Okay, and that ends chapter 8 and this section. So anyway, make sure that you go through the other examples. There are other examples in the textbook for practice. Make sure you go through them. Make sure you understand them. If you get stuck or have questions, bring those to class. We're going to be working on plenty of examples, so please make sure you bring your questions so we can answer them first thing in class and go over anything that you got stuck on. And also, by the way, you can email me if you get stuck, and I'll be more than happy to help you that way. But make sure you attach your work. So I can see it, and that would be, I can help you much better that way. So until then, have a great day, and I'll see you in class. Bye-bye.